Thank you so much, Sasanga, for the introduction. Hello, everybody. Oh, let me close the message that this meeting is being recorded. Okay. So yeah, I'm Yanis. I'm going to talk about some recent advances in self-supervised learning and measuring generalization, and its recent works that I've been doing lately at Naver Labs Europe. So my talk today is going to revolve around the idea of transfer learning. And transfer learning is this machine learning method where a model is developed for one task and then is reused as the starting point for a model on a second task, right? So we can learn, for example, model parameters using supervised learning for image classification. For example, we can use the ImageNet dataset with the class annotations that are provided. And then we transfer this knowledge or generalize to other downstream tasks and datasets. And this is a highly successful recipe, especially when the downstream tasks have very few data, right? And they're small. Now, the question that I'm mostly interested in is, can we learn transferable representations, but without requiring annotation? Okay, and this is what self-supervised learning is all about. The idea is that you learn model parameters on an unlabeled set, for example, ImageNet, but discarding the labels. And again, you transfer the model to downstream tasks and datasets. So self-supervised learning has deeply impacted the field of AI in general lately. Of course, this is because it enables utilizing unlabeled data, and it has revolutionized natural language processing. You probably have heard of models like GPT-3 or BERT. And the last, at least couple of years, is becoming a core component of most computer vision state-of-the-art pipelines, right? And people like Jan LeCun or Alyosha Efros have been vocal advocates of self-supervised learning for more than the last few years. So in self-supervised learning, there are no annotations, right? So we learn a proxy task that is self-supervised, which means that it's defined on the input data alone. And in some sense, we're learning aspects of the input data that are generally useful for downstream tasks. And the best part is that no human annotations are required. This means that we can use any available image for training, while we also have the flexibility to find the best starting data for the downstream tasks that we want to solve. For example, for medical imaging, we can probably more easily find unlabeled medical images rather than labeled that are very costly. So now one might think, does this mean that I don't need to care about what data I use anymore? And that is very, very wrong. No, you need to care even more than having labels, because things like this tend to happen. And what self-supervised learning does is it amplifies and encodes whatever biases exist in your data set, right? So there are no labels to guide what we learn. And the absence of labels usually makes researchers and practitioners look even less at the data. So always make sure you do your best to inspect and understand the data you use, specifically for, especially for self-supervised learning. Now, for self-supervised learning, we have to define proxy tasks to solve, right? And these are usually handcrafted and come in different flavors. For example, they can be predictive or generative. One can try to predict relative positions of patches from an image, or turn into grayscale and try to generate the color, for example. Other proxy tasks are contrastive, where one is effectively learning invariance to a pretext task. And a very successful proxy task, contrastive proxy task for visual representation learning has proven to be to learn invariance to image transformations. And by that, I mean data augmentation, right? You have an image, you pass it twice through two different transformations, which means you do data augmentations on that image twice. And then what you want is to maximize the similarity of these two versions of the same image, right? Although this sounds maybe simplistic, this is the task behind most of the most successful methods on the last couple of years for self-supervised learning. And however, this is a task that is tailored to visual representations, right? Where one can handcraft image transformations. To go beyond pixels, one can consider a more generic task, and that of learning a lower dimensional space that preserves the topology of an already meaningful input space. And we usually call this dimensionality reduction or manifold learning. Now, with all this in mind, here's an overview of what I'm going to talk to you about today. First, we will talk about how to improve the transfer learning performance of contrastive self-supervised learning. Then we'll talk about how we can use these recent advances in visual representation learning for the more generic task of dimensionality reduction. And finally, and since generalization is what we care about mostly for self-supervised learning methods, we'll talk about how one can measure a specific type of generalization, concept generalization, in a more principled way. So, okay, let's start with improving contrastive self-supervised learning. So for contrastive self-supervised learning, the proxy task that we want to solve is the successful one that I mentioned before, which is to learn invariants to image transformations, to data augmentation. And for contrastive learning in general, we need to define positive pairs and possibly negatives, now in a self-supervised way, right? So the positive pair is going to be two transformed versions on the same image. And this is not a new idea. It has been used in the past, maybe in slightly different contexts. So starting from a given image, we first perform two transformations, get two images, and then we pass these two images through the model whose parameters we want to learn to get the two features that can be seen as like this green crosses as data points in a high dimensional space. And let's arbitrarily call them query and key, okay? Okay, now let's do the same for negative images, and negative is any other image that is not this specific image, right? For this proxy task. And we pass all the negative images through the same model and get the red crosses as negative features in feature space. So in contrastive learning, we aim to bring the representations of the green crosses of the positive pair close to each other and push then, for example, the query far away from all the negative features. And to do that, we use the influency loss. And it's a very simple loss that reminds maybe some people the softmax loss. On the denominator, we have the dot product between the features of the positive pair. On the denominator, we have the sum of all the dot products with the negatives, right? And methods that you might have heard of like MoCHi or SimCLR use this loss and basically differ on how they treat their negatives. So where do the negatives come from? For SimCLR, you have a mini batch. Each image on the mini batch is transformed twice, and then every other image on the mini batch is negative for that given image, right? For MoCHi, it's a little bit more, it's a little bit different, where you don't just have as negatives the image from the current batch, but you store a queue, a memory with features from images from the last few batches and use those as negatives to contrast. And the key observation that led MoCHi to have a larger memory of negatives is that if we make this proxy task of augmentation invariance more challenging, we usually get representations that generalize better, and this has been shown in a number of papers. And how can we make the proxy task more challenging? We can try to find the most challenging positive pairs, right? Try to find the best transformations, for example, to do. Some people do that. Some papers have studied that. Or we can try to get more challenging negatives, okay? So to get more challenging negatives, SimCLR can increase the batch size, right? This is the only thing you can do with SimCLR. Your negatives are everything else in the batch. As long as you increase the batch size, you get more and more negatives. Hopefully, some of them are going to be more challenging. For MoCHi, you have the memory queue. So you can directly get more negatives by increasing the size of your queue. And this works at some point, but then after some point, we see that we're mostly adding non-challenging negatives. Okay, and the compute grows linearly. Yet what we saw is that some hard negatives do exist, right? The hard negatives are the ones that are close to the positive pair that affect the loss, the influency loss most. And we saw that these few hard negatives have a strong influence in the learning of the representations. Excuse me. So we had the simple idea. What if we mix the hardest negatives for each query and synthesize new hard negatives? And this is what we called MoCHi. The idea is what I said, mix the hardest negatives and synthesize a small set of new hard negatives directly in feature space and on the fly for each query. So the process is simple. For each query, you pick the top closest negatives. You randomly sample, for example, 2 of them, and you get a new point by creating a linear combination of the 2. We can push this a little bit further, where we can select 1 negative in the query and just create a new point by mixing the query with a negative, just making sure that we're kind of towards the side of the negative and not that close to the query. So the idea is that you do this a few times and you repeat it and you get S synthetic hard negatives. And these are loss terms that you add in the denominator of your inference loss. So we implemented MoCHi on top of the MoCHi-v2 approach that back then was the state of the art. And the algorithm is as simple as I described it. And the idea is that MoCHi has a very small computational overhead because we only need to compute distances to the new data points that we have. We have all the negatives from the queue. We add a few more, which is orders of magnitude less. So the computational overhead of MoCHi is generally small. Now let's talk a little bit about the experimental evaluation that we do. And this is generic for self-supervised learning, right? So for self-supervised learning, we're learning augmentation invariance. We're learning with the methods that I just described on ImageNet by discarding the labels, right? And this is a model that we get. And then we can do a number of things. We can freeze the model and learn classifiers on top for ImageNet-1K or other datasets, or we can take the model and use it as a starting point and fine-tune it for tasks like object detection or ISA segmentation with like Mascar CNN, for example. I'm not gonna present numbers. I'm just gonna give you highlights of the experiments. I refer you to the paper for actual numbers. So for image classification, what we see is that although MoCHi retains the strong performance of the baseline, adding hard negatives doesn't give you gains. It shows little or no gains in different cases. However, when you use it as a starting point for object detection and ISA segmentation, we see that MoCHi helps the model learn faster. You get very strong performance after 100 epochs of pre-training versus usually 200 epochs for other methods, while MoCHi is able to reach the performance of the baseline in 25% of the epochs. Moreover, the gains seem to persist after longer training, and these are results on like Pascal VOC and MS-CoCo on detection and segmentation. So there is further analysis in our paper, for example, analysis with a class label oracle, and some experiments that show that MoCHi ends up to some better utilization of the embedding space as it's measured by the metrics of alignment and uniformity from Wang and Isola. So the take-home message here is that you can synthesize hard negatives for a more challenging proxy task, and this leads to faster learning. And also you get performance gains for transfer learning over a very, very strong baseline. And there are some models available online, and you can find more information and experiments and ablations in our NeurIPS paper from 2020. Okay, so this was the first part. We talked about making contrastive learning better. Now let's talk about dimensionality reduction a little bit. So unlike general representation learning, where the encoder function has to learn to transform a specific structured input, for example, like, intensities in a 2D grid to a vector, for dimensionality reduction, we assume that we already have a meaningful vector space to begin with, okay? So instead of that, excuse me for that, instead of trying to go from structured pixel arrays to a vector, we're trying to essentially compress a meaningful space, and in practice learn a lower dimensional vector space that preserves, for example, the topology of the high dimensional input space. So why is this important? Dimensionality reduction is a very important method, and it's still used for a large number of downstream tasks in practice. So we use dimensionality reduction to compress representation. So because compact representations are more memory and compute efficient. Whatever we do after that is far more efficient. And although there's this trend for learning things end-to-end lately, that is learning the representation, learning together with the peculiarities of the downstream task, for example, dimensionality reduction, this can be something very hard or prohibitive for the majority of researchers out there. That is, one might lack the know-how. It's not that simple to fine-tune a large encoder. You might not have the GPU, the compute, or the data to do it. And in other cases, you might not even have access to the encoder. You just get some meaningful representations from a sensor, and it's impossible to handcraft priors to learn the encoder with. So even in the case of natural language, handcrafting priors is like really, really hard. That's why masking is what they usually use there. So for all these reasons, dimensionality reduction is still used in practice in many fields, especially like biology or remote sensing or even science. So here's a figure of what we want to do. Let's assume we have an input space of dimensionality, capital D, and what we want to learn is this dimensionality reduction function, this encoder that takes us to lower the dimensions. So when the output dimension is either 2 or 3, we have a very specific and very popular case is visualization. So for visualization, there exists a number of very good methods that specialize. You probably know DSNE or UMAP, or recently MD is a great one. However, such methods are highly tailored to visualization, and they really don't scale well when we have like millions of points, or more importantly, when the output dimension is not 2 or 3, right? They're made for this use case. So when we have, when we want to reduce the dimensionality to, let's say, more than a couple of dimensions, the most common approaches are the ones that we call manifold learning methods. And these are methods that are trying to preserve the structure of the input space in the output. And there is, like, for example, here we see isomap. These methods usually require some sort of eigendecompositions or heavy optimization solvers. And because of that, they don't scale well with dataset size. So if you have a few million points that you want to dimensionality reduce, you can most probably not use manifold learning methods when the output dimensionality is more than a few dozen dimensions. So what do we do if we have a large data set that we want to compress? Well, in practice, what everybody's doing is linear dimensionality reduction, and this is usually some variant of principal component analysis or PCA. In fact, PCA is something that is used in practice in production for large-scale systems, especially for search systems, and it's still actively used outside core AI for other applications beyond, for example, vision and NLP. But let's take one step back and take a look. Why aren't manifold learning methods scalable, right? And it is mostly because of the reason I just mentioned earlier, right? Some of them require propagation on large k-NN graphs. Others use complex optimization solvers, or others use eigendecompositions, right? And all this make them hard to scale. However, none of these things is an issue for methods like the ones that I was describing in the previous part, right? Where we have, a simple contrastive loss, or we solve it with stochastic gradient descent over mini batches. There's no scalability issues for the recent self-supervised learning frameworks that are usually used for visual representation learning. So the question we asked is, can we borrow from these recent advances in representation learning now to design a more modern dimensionality reduction approach? And to do that, we first need to borrow a simple and scalable loss, and we chose a very recent proposed loss called the Barlow twins. This is a loss that was created for visual representation learning. So you have an image and you distort it twice. As we said, distortion, I mean transform it twice, and you have a positive pair. But Barlow twins doesn't have negatives; it only has positives, and it's a loss function that is based on decorrelation. And this is a property that is really, really important for dimensionality reduction. And I'm talking about decorrelation of the output dimensions. Because of that, it's also a loss function that trivially avoids collapsing, and this is a very elegant way of avoiding collapsing. despite not having any negatives. There's no contrastive pairs, you just bring the positives close to each other. So let's look at the loss function, right? For the Barlow twins loss, you need to create this empirical cross-correlation matrix, and it's as simple as this. You have the positive pair, let's say that is ZA and ZB. The cross-correlation matrix is essentially the outer product for every positive pair over normalized representations across the feature dimension, right? So this cross-correlation matrix is D times D. And you do this for every positive pair in the batch, and you average over the batch, and you get one such matrix for the batch. And now the loss is based on this matrix and has two terms, right? The first one is trying to push the elements of the diagonal of the matrix to 1, while the second is pushing all off-diagonal elements to 0, okay? So what does the first term do? If we look at the cross-correlation function, you see that CII, for example, is the dot product between the I dimension of the positive pair. So essentially, the diagonal of this matrix is the dot product of the positive pair unrolled, okay? Therefore, what the first term does is maximizing the dot product of every positive pair, right? As we said before, we're bringing the positives close to each other in the feature space. Now, the second term practically says that I want every two dimensions of the output to be as decorrelated as possible, right? We want everything that's not on the diagonal to be 0. No correlation between the dimensions. Okay, so what is missing to create a dimensionality reduction method is a way to define positive pairs, right? And now we cannot use data augmentations to define positive pairs. We're in the generic case, and in fact, our only assumption is that we have a meaningful input space that we want to compress. So we have to use some sort of pretext task that is for generic input spaces, and we don't need to reinvent the wheel. There are many. You can add noise, or better, one can learn to preserve neighborhoods in the input space, like manifold learning methods have been doing. And this is what we choose to do. We create pairs by sampling nearest neighbors in the input space. Okay, let's put it all together in a figure to better understand. We have our encoder, right? This is the function that we care about, the function that we want to learn the parameters for. And let's say we have this batch of, uppercase D dimensional vectors. Through the encoder, we want to learn them to go to lowercase d dimensions. So let's create positive pairs by nearest neighbors in the input space. So on the left here, we see the input space. We see the input space, and we take a pair of neighbors from the input space and we pass it through the same encoder. We just break them into top and bottom. Half of the pair goes on the top stream, the other half of the pair goes in the bottom stream. That's why we call it also twin learning. And what we do, we create these positive pairs, and then what we add on top is the Barlow twins loss. And that's it. This is what we called TLDR, or twin learning for dimensionality reduction. And there's something here that I haven't talked about, and this projector, which is another decoder of sorts. This is a head that takes you from the output lowercase d dimensional space to a d prime dimensional space where you compute the Barlow twins loss. And this is something that also exists in the Barlow twins paper, in the original formulation, right? They just kind of hide it from the figures, but it exists. So this is part of the loss. It's been shown that it's better to compute this loss at a different space, and even better at a space of much higher dimensionality than the lowercase d dimensional space. So we use this projector, whose parameters we also learned during training jointly with the encoder. And then we compute the loss at the output of this projector at this d prime dimensional space. Again, not for encoding, and at this time, we discard this projector and we simply use the encoder, okay? And as we can see, the encoder can be anything. It can be a linear layer if we want. So let's put it all together. This is a very simple algorithm that TLDR does. So you start from every point and you calculate the nearest neighbors, and then you sample a mini-batch by sampling points and then sampling randomly one of the k nearest neighbors, right, for its point. And these are your positive pairs. Then what you do is you learn the parameters of your encoder together with your projector by optimizing the parallel twins loss on these positive pairs. And this is a very simple but effective algorithm, as we will see. Yeah, so to evaluate TLDR, we went and used it for a task that is close to our hearts and close to us, but it's also still using dimensionality reduction, right? And that's large-scale retrieval. And since TLDR is input agnostic, we experimented not just with image retrieval, but also with document retrieval. And note that this is a case where the output dimensions are usually 64, 128, or 256. And what is used in practice, even for state-of-the-art pipelines, is variants of PCA. For example, PCA plus widening, right? And this because of not only the scalability of PCA and widening, but also the effectiveness. It's really hard to beat this very strong linear dimensionality reduction in high output dimensions. So in order to be directly comparable to PCA and have the exact same encoding complexity, we also choose that we're going to use a linear encoder for TLDR, okay? So in terms of encoding, TLDR amounts to just simply a matrix multiplication. And the projector that we choose, though, is not linear. The projector we use is a 2-layer MLP, and the output dimension is much higher than the intermediate, the dimension that we care about. So again, I'm not going to stay too long at the experimental results. You can go to the paper that we have on ArXiv to see them, but only present some highlights. So for image retrieval, we started for a very popular recent pipeline, GEMAP, and we simply replaced the PCA and widening that is in there with a linear dimensionality reduction learned with TLDR, okay? And what we see is that, for example, at the common Oxford benchmark for 128 dimensions, which is a very common dimensionality that you use in downstream tasks, is that you can get gains in MAP, and you can also match the uncompressed performance with 16 times your dimensions. And these results also persist for the Paris dataset, for example. So for document retrieval, we got some features from a recent method called ANCE, and it's some features based on BERT, right? So you have these features, and then we do, again, linear dimensionality reduction with TLDR, and we compare it to PCA for this task of argument retrieval on a dataset called Arguana. And again, what we see is that we have consistent gains over PCA, and we can match the performance of the full representation using just 4% of the dimensions. So there's a number of ablation and discussions in the manuscript, but we also, of course, compare to manifold learning methods, and for that we need to use smaller output dimensions. But what we see is that for any manifold learning method we tested, TLDR outperforms all of them for when the dimension is like 8 or more. And a note here is that the second best was linear dimensionality reduction or variants of linear dimensionality reduction for any dimension of 16 and over. For these results, for example, at the Oxford dataset. So what are some advantages that TLDR has is, first of all, generality. It can compress any meaningful vector input space without any further assumption. Of course, this is shared with dimensionality reduction methods in general. But now with TLDR, you can also have many different types of encoders. You can have a linear encoder, you can have factorized linear encoder, or an MLP. TLDR is simple. It's pretty robust to hyperparameters, and we also found that hyperparameters transfer across tasks, so it's easy to tune. And also the Barlow twins loss is a loss that is easy to optimize in general with the Lars optimizer, and it has no negatives, and loss hyperparameters were literally transferred from the original paper to our use case without a problem. TLDR is an inherently scalable method, right? It's learned by mini-batch stochastic gradient descent. It's very GPU friendly, and as we saw in the paper, we have very high resilience to approximate nearest neighbor. So you can approximate the nearest neighbor step one without problems, without losing performance. and it requires no graph propagation. Although we do the KNN computation in the beginning, we don't even need to store the graph. We just need to sample pairs, right? We never propagate anything on this KNN graph. So we believe that TLDR can be a very useful tool for a wide range of tasks and a lot of people, way beyond computer vision and NLP or AI. And this is why we wanted to make it easy for people to use it. So we publicly released code that has this API that scikit-learn has. It's a very common API. So you have your function, you just define your function in 3 lines. Like you use fit, you use transform, and that's it. You can use it out of the box, even with default parameters. It's really easy to use. We have code there. I encourage people to try it if they're using dimensionality reduction, and if they're using PCA, there's a good chance that you're going to get better results with TLDR. So to sum up, TLDR is a scalable dimensionality reduction method that has strong performance on most retrieval tasks. We tried it. We have many tasks in the manuscript. We have easy to use code publicly available. And so what is it suitable for? Because it's not suitable for everything. It's suitable for dimensionality reduction, possibly linear if you care about scalability of test time, right? To a few hundreds of dimensions. What is TLDR not suitable for? It's not suitable for visualizations. You can do visualization. We have some in the paper, but it's not suitable for. There are much better methods for visualizations. And it's also not suitable for representation then, right? If you can handcraft priors, do that. If you can find other ways of having more meaningful priors for your task, please do that. It's better to do it. Okay, and this is a paper that we published on ArXiv recently, last year. Okay, let me go to the last part of this talk, which is on measuring concept generalization. And what is concept generalization? Is the extent to which models that are trained on a set of seen visual concepts can be used to recognize the set of unseen or target concepts. So the question we're asking is a model that is trained to recognize cats a good starting point for then learning to recognize dogs? And how about corals, right? Or in general, does it matter what is the semantic relationship between the training and the transfer concepts? So our hypothesis is that yes, semantic distance between training or seen and target concepts impacts generalization performance. And we want to measure that, right? We aim at quantifying and measuring this hypothesis in a principled way. So we claim that when learning on cat images, it's easier to transfer the knowledge to dogs rather than to like sea creatures, for example. So our goal is to design a better benchmark for measuring concept generalization. But first, let's look, how do we measure concept generalization right now? Okay, so what we do now, we usually learn model parameters on a data set. Usually we use the ImageNet-1K dataset for that, with or without labels. And then we transfer the knowledge and measure performance in many other datasets, right? We usually learn linear classifiers to many other datasets, and yeah, like food, CFAR, cars, aircrafts, Pascal VOC. What is important is that currently is really unclear how the concepts in these datasets relate to the concepts that are seen during the training, okay? Let's take Pascal VOC, for example, because it's small. What we're doing is we're learning model parameters on ImageNet-1K, right? These are the seen concepts. And then we have the 20 classes of Pascal VOC, and these are the target concepts. And these are the 20 classes of Pascal VOC. So if we look closer, there are classes that are really the same from ImageNet-1K to Pascal VOC, right? Others are more or less, you can find the correspondence, right? Minibus and school bus and trolley bus probably all are ImageZoo bus, right? Others are not so clear, but again, ox should be like really close to cow visually, right? Also bison a little bit further. How can we make this more principled, right? We want to design a better benchmark. And to design a better benchmark, we need the following, right? First, we need a large set of concepts. And second, we need a controlled setup where we know for sure that the training concepts are disjoint from the unseen concepts. And we also would love to have a way of measuring how far these concepts are, right? In some semantic distance, for example. So to do that, step 0 is to pick a large data set. And we picked the ImageNet-21K dataset, which is a superset of the famous ImageNet-1K dataset. Usually when people refer to ImageNet, they mean the ImageNet-1K dataset. But this is a subset of this larger 21K dataset with 14 million images and 20,000 concepts. And the cool part is that ImageNet-21K was created so that its concept corresponds to a scene set from this handcrafted semantic hierarchy called WordNet, right? Okay, so let's first define a disjoint set of seen and unseen concepts, and this is a very easy choice, right? Since we have ImageNet-1K being a subset of our data set, this is going to be the seen concepts. This is what everybody is using anyway for learning their new architectures or new self-supervised learning methods. So these are the seen concepts. We remove them, we remove pathological concepts, we remove concepts with a few images, and everything that's left, which is approximately 5,000 concepts, are concepts that are now eligible to be the unseen concepts for our benchmark, okay? And now remember, all ImageNet concepts are part of the WordNet graph, and we can therefore use metrics on this graph to define semantic similarity, and we used out of the box the link similarity, which is part of NLTK, and this is a way of measuring semantic distance between one concept and another. In practice, we found that this choice of metric was not crucial, and as we saw in our paper, you can substitute this for word2vec, for example. Now, the first thing we do is to extend the similarity to work not from one concept to another concept, but to cover the case of a set of concepts to one concept. Why? Because we have a set of seen concepts during training that we care about, and we want to see how each of the unseen concepts relate to all the seen concepts as a set, okay? So we extend it in a very simple way. For each one of those 5,000 unseen concepts, we just get the maximum link similarity from any of the seen concepts on ImageNet-1K. And then what we do is we simply rank all these 5,000 unseen concepts with respect to their semantic distance to the scene. So as we go further, we have more distance. As we're closer, it's like more similarity. And we have this ranked list, and then we chunk it. We cut it in 5 chunks. We split it in 5 what we called concept generalization levels. Okay, now, the important thing that we see here is that each level contains concepts that are on average, right, semantically further and further away from the seen one. So concepts in L1 in the first level, first scope level, are closer to ImageNet-1K than concepts in L2. Concepts in L5 are, according to link similarity, the furthest from the seen concepts, right? What we also did is like, we had 5,000 more or less concepts. So we made each one of these CoG levels to be as big as ImageNet-1K. So each one has exactly 1,000 classes and more or less as many images as ImageNet-1K. So even accuracy numbers could be comparable between the levels, the 5 CoG levels and ImageNet-1K, right? So this is the ImageNet-CoG benchmark. We have now a sequence of 5 data sets of unseen concepts, each with increasing semantic distance to the seen concepts. And the evaluation protocol is now the following. We first use a model that is trained on ImageNet-1K out of the box. We freeze it and we just use it as a feature extractor. And then we learn linear classifiers using those features, okay? And the cool part of this protocol is that if somebody puts out on the internet a pre-trained model on ImageNet-1K, we can out of the box evaluate it on our benchmark. And this is what we did. We evaluated, I mean, this work is now a little bit old. There's maybe soon there's gonna be a newer version out there with even more models, but we found the best models we could get at that time. And it's 30 models, and we compared all of them together with the out-of-the-box baseline ResNet 50. We focused a lot on self-supervised models because this is the area we care about. We have other models that have, for example, visual transformers or different ways of regularizing training with label-associated augmentations like cat mix or mix-up. So now, again, I'm going to present highlights from our study because I don't think I have a lot of time, and you can find more in our paper. In this very dense figure, so in this figure, we first, on the y-axis is accuracy, okay? And on the x-axis are the datasets. First is ImageNet-1K, right? And then is the 5 levels. So as we go up the x-axis, we go to further and further to concepts that are further and further semantically than the ones in during training. So even without looking at the numbers of this chaotic graph, we see the trend, right? We see that our hypothesis is verified. It is harder to generalize to semantically distant concepts. But now let's try to make this graph a little bit more easy to read. And to do so, we take the black line. You can probably see the black line somewhere in the middle there. This is the line of the ResNet 50 from Torch Vision out of the box. So we will take this line and flatten it, okay? Like this. And now we are gonna measure relative accuracy to this baseline ResNet 50. Okay, this is for clarity because it's easier to see things this way. Okay. First, let's look at self-supervised learning methods because we like them. What we see is that, okay, of course, on ImageNet-1K, on the leftmost part of the graph, all self-supervised methods are below the supervised case, right? Which makes sense. When we're testing on the scene concepts, it makes sense that having labels during training would help a lot rather than just learn classifiers in the end. But then we see, as we move up the levels and we go to further and further semantic concepts, more and more self-supervised learning methods outperform the baseline, right? It's clear that self-supervised models do great for concept generalization. Now, when we look at different regularization methods, we see two main things. First, that model distillation generally improves CoG performance, generalization performance for concept generalization. Most distillation-based models that we tested perform really well. And the other interesting thing is that methods like cat mix and mix-up and manifold mix-up all show gains on ImageNet-1K, but then these gains don't transfer when you generalize. So we kind of overfit to the training task, not the training images, but the training task with such label associated augmentation techniques. The figure for different methods and different architectures is a little bit more dense here. In general, we see two things. First of all, that visual transformers have much higher gains on ImageNet-1K than they do on the levels. Many for like similar number of parameters, the gains like kind of disappear. Then what we also see is, of course, that having larger models helps, right? And that models that are found via neural architecture search performs really well in our benchmark. So to sum up, the best ways of achieving high concept generalization performance, and you can see this, like these are the highest performing methods on level 5, are methods that are models with better and larger architectures, distillation models, self-supervised learning models that surprisingly surpassed even other models that are trained with 100 million extra images. But then it also helps, right? If you have all the models that were pre-trained with additional data that were kind of, it's an unfair comparison of sorts, they perform really well. So I refer you for more of the study in our paper. It was presented at ICCV. So the take-home message here is that ImageNet-CoG is a new benchmark that enables measuring one specific aspect of generalization, concept generalization, in a controlled way. And it consists of a sequence of levels of unseen concepts from ImageNet-21K, each one with increasing semantic distance to the seen ones. And the seen ones are ImageNet-1K. And because of the seen ones are ImageNet-1K, it was easy to test many models out there out of the box. And it is very easy. We try to make it easy. We try to make it easy for you to test your ImageNet-1K model. So if you're working on architectures, visual architectures, and you have models that are trained on ImageNet-1K, you can go to our code base and just use our scripts and measure the performance of your model. So that's it. To sum up, at this talk, I first talked about how we can improve the transfer learning performance of contrastive self-supervised learning by synthesizing hard negatives. And the second part, I talked about how we can borrow from these recent frameworks to have a more modern and scalable dimensionality reduction method. And then in the end, I presented ImageNet-CoG, which is a new benchmark that aims at measuring concept generalization in a principled way. And all this work is not just my work, is work with a number of colleagues and students at Naver Labs Europe. All the works that I presented are with Diane Larlouche, for example, and then two of the three are with Bulent Sarilis, who is a student who is co-supervised with Diane, and Kartika Lahari from India. And then Carlos, John, Noe, and Philippe are also co-creators of some of the works that I presented. So I presented all this on behalf of all these great people that I thank so much for the amazing collaboration we have, which brings me to how nice it is to be at Naver Labs Europe. So it's true. So at Naver Labs Europe, we have teams focusing on computer vision and 3D vision, and we have a strong push now on AI for robotics, as well, of course, as AI for all the digital services of Naver. And we have many researchers and many publications. We publish at the top places. And we have a lot of collaborations with a lot of other teams like Naver in Korea, or collaborations with top tier universities. And INRIA, for example, we have collaboration with INRIA in Grenoble. And we have research scientist positions open, and we have research internships that are possible year-round. So check out our webpage, and if you find some research or researcher resonating with you, please talk to us. And here's the researcher that might resonate with you. So here's my research interest. Yeah, I had this here because I also want to mention that I did my PhD in Athens with Yannis Avritis, who was part of this team. And we were working on retrieval and clustering and nearest neighbor search. And this was the beginning of my love affair with research because of Yannis and the great atmosphere we had there. And then I was in the US, and I was working on vision and language and large-scale search and architectures, and then video, and then long tail. And now I'm focusing on self-supervised learning in general. What I'm really interested in is to how can we learn with limited annotations and models that are expressive, visual representations that are expressive, and systems that are adaptive, right? And can be reused. Okay, so as a teaser, this is how our offices look in the countryside of France. Not that countryside, but they're beautiful. And yeah, thank you. Any questions are more than welcome. I hope I didn't go very over time.
It was awesome. Thank you for the talk. If you have any questions, feel free to unmute and
Maybe I was going too fast for questions.
I actually have a question / comment, I don't know. First of all, thanks for the talk. It was amazing. Regarding the concept, the generalization problem. So if you want to understand calculating the hierarchical distance in the graph and so on.
Konstantine,
I think you have a problem with your headphones. There's a lot of noise coming in.
yeah, Konstantine.
Is it better now?
No, I think you can just remove it and.
So if I understood correctly, you were talking about CoG, and you were talking about something like this. Wait, sorry. Like something about the the link similarity. Did you have a question about that?
Better now or not?
It's hard to understand what you're saying. I'm so sorry.
Not better.
No, it's you can just remove your headphones and then yeah.
That's fine.
Can you hear me now?
No,
Yanis, there is a question in the chat box that might be easier to answer while our friend tried to fix this problem with the microphone. It sounds like a robot is attacking Earth.
So Yanis, there is a question in the
course.
chat from Anton.
Okay, let me
He
try to
says
find the
that-
chat.
Yeah, sure.
Okay.
If you want me to read it, I could, but yeah.
Okay. Is the question, at some point, how do you ensure that the negative should be further than the positive? After tampering the original image too much, could another untampered image be closer to the original image in the visual semantic space? That's a very, very good question. And to take it one step further, if what we want to solve afterwards is image classification, note that for this specific, let me go also try to go back to a figure that shows all this. Like here, in this figure, every other cat image that could be in the dataset, and in the dataset we might have, you know, the next frame of the same video, right? This is a negative, while a highly transformed version of the same image is a positive. So what you're saying is you don't ensure it. You actually have maybe even bigger problems like this. So the fact that this works well was how we really started this MoCHi project, right? We wanted to try to break this because we were saying that maybe, you know, you contrast, you know, this specific cat with every other cat. So how can you learn a good cat representation by doing this? Well, it turns out that on average, it doesn't matter that much. And that the representations you learn, this invariance to this augmentation gives you a good enough representation to do almost anything you want to do after, including classification on the exact same data set that you're training on, which is a very biased test. But it's a standard test that everybody's doing, right? We take ImageNet-1K, we remove the labels, we learn augmentation invariance on ImageNet-1K, and then we test how well we do for classification on ImageNet-1K, and we do very well. And yeah, in the end, I would attribute all this lately, you know, to the dimensionality of the output space, which is pretty big, and you can do kind of whatever you want. But yeah, I hope this answered the question. Okay.
I have a question regarding the TLDR method. So I quite didn't understand, like, do you use a off-the-shelf, a network to kind of come up with the high dimensional feature, and then you put it into the Barlow twin architecture? So how is that?
Yes,
usually?
Exactly. So this is a very good question. So this is the difference, right? We don't want to do representation learning. We just want to learn to compress an already good space. And I know it's confusing because our test in the end is like on top of image representations, right? But it's just proof of concept, and it's just, we still use PCA there. So wherever we see TLDR as a replacement for things like PCA. If you're using PCA, it means that you somehow found yourself with a set of vectors, and these vectors are too large for what you want to do. So you want to reduce the dimensionality. So this is where you should use TLDR. Okay. Does this answer your question? It can be anything.
Yes. I have a follow-up on that actually. So when you actually construct the positive pairs, is there a possibility of having noisy pairs? Because let's say, for example, I think you said that you use retrieval as your task, right? But for example, if you just use ImageNet, where there might be like multiple objects in an image, and then you kind of use an off-the-shelf network to come up with a high dimensional feature, and then construct the positive pairs, would that kind of lead to noisy pairs? So I'm just curious.
This is a very good question. So so actually you probably have a lot of noisy pairs, right? Is how much you trust your input space. So what I wanted to show you here is, first of all, you have to select the hyperparameter, which is K, right? I'm sorry, these are my extra slides. So I'm trying to find, okay, yeah. We're varying the number of neighbors K that we use. So first we see that, of course, it cannot all be correct, right? We're getting 1 or 25 neighbors to sample from. And in most cases, it works well. Many of them are probably wrong, again, in terms of your downstream task. So if this is like Oxford buildings, many of the 25 neighbors of that specific building that you pick to create a positive pair are a different building. Similar to the self-supervised learning with augmentation invariance, all these errors seem to be tolerated. And another thing that I wanted to show is that you can also use very approximate nearest neighbor, like you can do PQ and compress and do nearest neighbor search in the input space with much smaller representations, and your performance starts to drop after 99% of compression, right? So it's a very good question. There is a lot of noise in the pairs, but it seems that there is robustness with this contrastive learning functions. It's a very good question and an open research question too.
Thank you.
Sorry, I don't have a better answer.
No,
Hey, I also had a question on TLDR. There's one thing that I didn't quite understand in your architecture that you just showed. So there's a Barlow loss that is applied on some kind of feature space. So those B just before the loss. And so basically your loss is trying to make this representation quite nice. Somehow every feature, every dimension will be orthogonal, I mean, because of this loss. So I think, I mean, from what I understood, the representation that you learned that should be very nice is the one just before the loss. But actually you're using a lower dimension before. So I don't really, can you give us a bit more insight on that?
Thank you, Ronan. So first of all, can you see my pointer? Can you see my mouse pointer?
Yes, yes.
So this is the representation that we care about. And you're touching a very interesting subject where we're talking about how we are decorrelating dimensions, but we're not decorrelating the dimensions that in the lower dimensional space that we care about. We have this projector, which in practice has like millions of parameters that takes you to a output dimensional space that is usually as big as the input, if not bigger. And what we're decorrelating is something very indirect, which is the dimensions on this output space. So it's of course like I probably also went really fast. It's hard to understand this. On the one hand, the Barlow twins loss is some sort of like soft whitening. It's doing this decorrelation, but it's doing it in a space that is not the space we care about. And it's not computed in the space that we care about. So again, this is an open research question. We've seen it a lot in self-supervised learning that you add this projector heads for learning that are very important for contrastive learning that you throw away after, and going through this, which is usually an MLP, through this MLP to this other space, you still learn good representations for what came before the MLP. And what I think is very important, and you can see it also from appellations, is that there is some sort of bottleneck effect here, right? You go from a higher dimension to something smaller, and then back to something big. And this is some sort of autoencoder in practice. The fact that this bottleneck effect happens, I think is very important for whatever happens in the end to translate all the way down and to the lower D dimension representation. But again, it's also a mystery to me and probably to a lot of people, everyone.
Okay, so maybe the magic might come from the autoencoder thing, and maybe not so much from the loss. We don't really know which one of the two components could be. I don't know.
Yeah, that's true. So there is a good paper. I think an ICML 2021 best paper was about something like this, about these projectors in contrastive self-supervised learning, right? By Yandong, I don't want to, but you can check it. But it's interesting to say, by the way, that PCA is also an autoencoder. It can be seen as an autoencoder where you have a linear encoder, and then the projector is the linear encoder transposed, right? So I think the fact that you're going to a very high dimension out here is far more important. You're not trying to reconstruct your input. You're going to a very high dimension and then you decorrelate it. Yeah, any of this could have this effect. By the way, we have comparisons where we drop the projector and it doesn't perform well at all. And in fact, if you drop the projector and you do contrastive learning on this lowercase d dimensional vectors, this is the Dr. Lim paper by Jan LeCun. I have to say that this paper is essentially a combination of two papers of Jan. It's like his Dr. Lim paper, where we throw away his contrastive loss and we put the Barlow twins loss, which is another paper that Jan LeCun is in. And yeah, is interesting. Yeah, but I don't remember now what I want to say. Yeah, that's what I remember. Renan, yeah.
Thanks. I had another small question about MoCHi. You said that you're looking for closer images, but is it only in the batch, or is it all over?
Yeah, that's a very good question. I passed all this in one sentence here, which says we implement MoCHi on top of MoCo v2. So we followed MoCo. MoCo is a work by Kaiminke and others, and the idea is that the negatives come from a memory queue. You have what's called the momentum encoder that has is a second version of the model that is learned with a very high momentum, so that representations from previous batches are kind of comparable with the current representations, and all the negatives come from a long memory queue from the momentum encoder. So essentially, in our baseline, which is what was state of the art at March 2020 and May 2020, when we're submitting that paper, the memory queue is like 64,000 negatives, and what we're adding is 1,000 extra synthetic negatives. So the computational cost is for each query you need to also do 1,000 more dot products and add them to the negative logics. Does this make sense?
Yeah. Okay. Thanks. Thanks a lot.
Yanni, thanks
Yes,
a lot
Yanni.
for your talk, and congratulations on all this work. So I also have a question on TLDR. It's about supervision. Usually, sometimes the boundary between supervised and unsupervised is quite subtle. I mean, with ways that do not require any human effort, it is possible to acquire some labeling that is pretty reliable. It's like supervised with a little noise. And one example is the structure from motion dataset that is used to fine-tune for image retrieval. So my question is on the experiments you have on image retrieval, where the pipeline usually is training something supervised on ImageNet, then fine-tuning on some retrieval datasets with landmarks or so. And in this case, one of the dimensionality reduction that is pretty good is supervised PCA and whitening, where the supervision is on the same data set that is used for fine-tuning, like structure from motion. So have you used, and I think this kind of supervision could be used to define your positives over there, instead of looking for nearest neighbors. Have you done such experiments or compared with this supervised whitening?
This is a very good point. We never compare, no. So in GEMAP, which is a work from one of my co-authors in this paper, John Almazan, they didn't even use supervised PCA. And then at the same time, I was recently working with Yorgos Tolias's recent paper called How, where again, he's learning the PCA in an unsupervised way. So what you're saying makes a lot of sense. But none of the two, pipelines that we were looking into was learning it in a supervised way. So we never thought, but yeah, it makes a lot of sense. And the other thing that I thought you would say is that what makes a lot of sense here is your other works on propagation on the manifolds, right? So we can get, I've discussed this also with Yorgos. It makes total sense to even out of the box get better positives for this. Both make a lot of sense. What we try to keep it is as simple as possible for this paper, and try to make it as universal as possible in that regard. Of course, this method is as good as your input training data, right? If your neighbors in your input space don't make any sense, what you're going to get is not going to make any sense as well.
So the dataset that you used to learn the dimensionality reduction was what in this case?
Google Landmarks. Google Landmarks. Yeah. But we wanted to show scalability. That's why we didn't go with SFM. We wanted something big to show that this scales,
Right, but it was without the labels, right?
Yes, of course. Okay. But and the graph I showed, it's in the appendix. The graph I showed here, when we're varying the K, is on Google Landmarks. So Google Landmarks, I'm not really that familiar with the peculiarities of that data set, but I'm sure that some of the classes have way less than 10 positives, right? So many of those neighbors in many cases are erroneous, are like not the correct thing for the task, which is landmark retrieval in this case. So yeah, it was surprising how flat this curve was up to reasonable numbers of K. Yeah.
Okay, thanks.
Thank you, Ian.
May I ask a question? Hi, Yanis, it's Makis. Nice to see you. And thank you for the very interesting and informative talk. I also have a question about the TLDR.
Hi,
Can you go back to the slide, the whole structure? It was more technical about the Barlow twins loss. So how do you actually train this? Because I think with stochastic gradient descent, you're not most probably you will not have a sparse matrix as output. So do you care about having actual zeros out of the diagonal, or it's just enough to have relatively small values?
This is a good question. So this is a large matrix, but it's not that large. It's even if the output dimension is 8K, which is in like our biggest. I think we tried 16K. 8K by 8K is 64 million parameters, right? If I'm not mistaken. Well, assuming that they have trained this loss on top of huge VITs or CNNs that have many more million parameters already, just having this matrix there is nothing, more or less. Plus, the projector is an MLP that has like many parameters. The projector it's a funny case. I don't know why they chose to not show it in the Barlow twins paper, but it exists in Barlow twins. And the parameters that the projector contains is many more than this matrix, right? It's an MLP from 2K to 8K, from 8K to 8K, from 8K to 8K to is many millions of parameters. So we never had an issue with memory, for example, or considering considering that we don't train any. The encoder is a linear layer. Our encoder is tiny. It's 2K to 128. Is very few parameters. All the parameters in the projector, and and then this cross correlation matrix is huge, but it never really mattered. And it's, as they say in the paper, you can see this decorrelation as some sort of soft whitening. And there are other papers. So there is the paper that's called Whitening for Self-supervised Learning by some people from Trento, I think. where they do actual whitening there, and it's kind of trying to decorrelate it fully. And this performs better with this soft version. So we don't really care about turning it all to actual 0. You're just trying to minimize it, and it's good enough. And again, this decorrelation, I have to repeat that it happens in a very different space than the one that we care about. All this 150 million parameters are thrown away in the end, and we keep only the small linear encoder, or non-linear. We have experiments with NLPs there too.
Okay, thank you.
Thank you, Mikey. I couldn't see you, now I can see you. Thank you for joining.
I think Constantinos has a question in the chat, so if you can just answer that as well.
Yes, so I saw it. So in CoG, you create and separate the concepts by calculating the hierarchical distances of the graph. This graph WordNet is basically a handcrafted one, and it induces biases in the first place, correct? So have you thought of ways of mitigating some issues in the ranking of the course? This is a very good question. And let me just also note that WordNet is not a clean graph. It has a lot of issues. It has a lot of things that don't make sense. Yeah, so so it's not a hierarchical distance, by the way. Let me go to that and explain a little bit more. I know I went very fast in many places. I'm sorry for that. So the link similarity is IC is the information content, basically tells you how big the subtree under a node is, or something like this. And it compares the information concept of the two nodes versus the common, less common, the common ancestor anyway. So it does infuse biases, but we based our hypothesis that semantic, whatever that might mean, semantic similarities affect. And these are not visual similarities, right? They're semantic similarities, and whatever induced biases are from WordNet, it was in the end created to respect semantic distances up to some point, of course. Of course, it's not perfect, but we never thought of mitigating such issues just because we said that we have to trust something. So we said we can maybe trust WordNet because it's handcrafted by whatever linguistic people who work on linguistics. So yeah, it was also that we had a number of studies, excuse me, in the supplementary material of that paper. There is a number of issues with the ranking. Having said that, it's definitely not perfect. It's much better than just randomly taking 20 data sets and just checking the average, right, without caring how far things are. This is a little bit more principled. Is the best way? Probably not. And I don't know if you have any ideas on how we could mitigate further these biases. That would be great. In earlier versions of this paper, a lot of reviewers were asking, why don't we use a baseline with visual similarity, right? And it's because we didn't want to. We didn't want visual similarity to guide. We want to learn any measure on visual similarity will have the inductive bias from the model that we use to compute visual similarity, right? So at least now we have these biases from WordNet, which are a little bit further. I think it's not a very clear answer, but yeah. I'm sure you can talk, we can discuss, because I mean, your headphones don't work well.
I guess we've been covering a lot of topics, right? I mean, those 3 things plus those many questions and great answers. This is just beautiful now. Some time has passed. Is there any last question to ask? Last chance.
Last chance, everybody.